supposed to conduct 2 sessions today, which are pretty heavy in nature. So factor analysis, in fact, the exploratory part of factor analysis in itself is quite heavy. So we are adding confirmatory factor analysis also with it. So I will try to keep it as simple as possible. And we will just go for one hands-on, one example for EFA and one example for CFA also. But before moving on to the use of SPSS, which is the primary focus of this particular workshop, let us just have an understanding about the fundamental understanding about the EFA and CFA. Most of you probably, those research scholars or teachers or supervisors who are focusing on quantitative research, probably they have heard about this term, and probably you have also used it. So it will be, so for those people who have already used factor analysis as a multivariate technique, it will be a kind of, refresher kind of a thing. And you will be very surprised to know, if I get time, I will just share with you a few things that this is pretty weird, because when I first encountered it a couple of months back, I was so shocked rather than surprised that the qualitative data also factor analysis is being applied. And they have given a very wonderful name to that also. It is called FATM, or the factor analysis topic modeling. And a lot of softwares which support the visualization and factor qualitative data analysis technique, they can take up this factor analysis for qualitative data. Qualitative data like interview transcripts, etc. So the principle remains the same, the extraction process remains the same. Anyway, if I get time, we can have a small discussion on it. But let me just take you through a presentation. Just give me 1 minute to share the slide.
Sir, you are not audible. Okay. No, sir. Again, something. Something problem with the wire, I guess.
Yeah.
Oh, yes, fine, sir.
Am I audible now?
Yes, sir.
Okay. So if you can say whether the screen is visible or not.
Visible, sir. Okay,
thank you. So the first thing that we want to share is the exploratory factor analysis. So let us have a quick understanding about the difference between the dependence method and the interdependence method, because we all know that factor analysis is one of those multivariate applications which uses the interdependence technique. So in a dependence kind of a method, we all know that it's a kind of a multivariate technique, and it is appropriate to use when one or more of the variables can be identified as dependent variables and the remaining as independent, so that we can establish a kind of a relationship. We can assess the strength of associationship between them, and we can go for predictive modeling, etc. So a predefined set of dependent variables and a predefined set of independent variables, that makes up for this particular framework of dependence method. So the type of dependence method normally we use for application to assess the hypothesis or to test the hypothesis are the regression analysis or the MRA, the multiple regression analysis, or for classification we use the logistic regression or the conjoint analysis for segmentation, canonical correlation. We use the discriminant analysis to we use the MANOVA, we use SEM, the structural equation modeling, which are all the dependence techniques. Now, in contrast to these, if we see what the interdependence technique is offering us, it's also a multivariate statistical application in which a whole set of interdependent relationship is examined. So basically, no single variable is identified as a dependent or independent kind of a variable. So there is no preconceived notion held by the researcher that there is a set of, existence of a set of dependent variables or a set of independent variable. So what exactly we do in these kind of cases, we analyze all the variables in the data set simultaneously. The major goal for this particular method is to group things together. It is essentially a data reduction kind of a technique. It crunches the data. It simplifies data, in fact. No one variable is predicted or explained by the others. And the kind of interdependence technique we use are obviously the focal area of today's session. It's the factor analysis, the cluster analysis. Perhaps you have done a session on cluster analysis also. Perceptual mapping, those who are from the field of business administration or from the geography, probably you have heard about perceptual mapping, which is a quadrangular mapping based on dimensions. Multidimensional scaling is one of the interdependence technique which is heavily used. Correspondence analysis also, again, it is a dimensional spread which we normally use for either mapping the behavioral pattern or for brand distributions in the market, etc. This is the classification of multivariate methods. So if we start from the very beginning, if the number of dependent variable, if we start from there, say if the number of dependent variable, if it is minimum 1, then obviously we move towards the dependence methods, and there are a number of dependence methods based on the nature of the data that you are handling. And if the number of dependent variable is 0, then obviously we are moving towards an independence method. So under independence method, we have seen that the factor and cluster and perceptual mapping and MDS, these are various techniques which can be used. So factor analysis is one of these interdependence techniques whose primary purpose is to define the underlying factor structure among the variables in the analysis. Now, I will just make a brief explanation of this. Let us see what EFA has to offer. EFA could be described as an orderly simplification of interrelated measures. Now, if I combine these two, the concept of factor analysis and the concept of EFA, it does two things. One is it simplifies, it reduces data substantially to make it manageable. And number two, it identifies the underlying factor structure of an observed set of variables. Now, you see, when we are conducting certain research work, particularly in the field of social science, we often, are confronted with certain kind of measures, certain kind of constructs, which are very difficult for measurement in a direct way. Okay, so direct measurement may be problematic. Say, for example, if I want to analyze the behavioral pattern of an individual, say, as a teacher, if I identify a particular person, a particular student as an introvert, or a particular student as an extrovert, there is no direct measure for introvertness or extrovertness. So these can be at least, or at best, certain kind of a latent construct or unmanifested constructs, for which I need to have a kind of a surrogation technique, an indirect kind of a measure or a proxy measure, with the help of which I can actually hold a certain understanding about this. Although they are manifested in several ways, but they are very difficult to measure directly. So I need to understand whether a student is an introvert or an extrovert based on certain behavioral pattern of that particular student. Say, if I study the interaction of that particular student in a group, the way he interacts in the class, the way he interacts with other fellow students, the way he participates in certain programs, the way he leads his or her interpersonal communication skill, etc. So these will be the observed set of variables, so observed set of patterns based on which I am supposed to, as a teacher, assign a dimension for this particular student to be either an extrovert or an introvert. So for these kind of problems, so for these kind of issues, the EFA technique is ideal. Okay, so if I want to search the underlying factor structure, which is lying underneath a set of observed variables, I can do so by applying this particular technique. And simultaneously, this technique, as I have already said, it is an approach for data reduction. How data reduction is taking place, we will understand it later. But why data reduction is essential? Because when we are collecting data with regard to certain observed variable, we are not sure about which of these observed variables will be an exact measure for something which is hidden, something which is latent, something which is not manifested properly, something which cannot be directly measured. So as a researcher, we are basically exploring all such observed variables which can contribute to the construct of a latent, kind of a variable or an unmanifested construct. So the number of observed variables that a particular researcher takes into account or brings into the framework is quite large. Okay, it can be 50, it can be 60, it can be anything. So it becomes very difficult for a researcher to handle all these variables at a time. And at the same time, you are not very sure that how many variables are not that important to portray that particular latent construct or to characterize that hidden construct. So in a data reduction technique or in a data reduction process, the primary objective is to identify those observed variables which can exactly define the latent construct, which can exactly characterize that latent construct. So on the basis of the correlation between the observed variables and extracted factors, and based on certain cutoff values that we as a researcher assign to this entire process, in normal cases, we call them factor loadings. So probably you have seen those who have already conducted factor analysis. We are, keeping a baseline figure of say 0.6 or 0.7 to make the model more robust. So you will find that the correlational values between the observed variables and the extracted factors, which are having minimum of 0.6 and more, they are retained as the most potent observed variable that can best describe those latent factors. Okay, so this is a technique with the help of which, from a distributed set of observed variables, we are trying to identify the factor structure. Okay, and at the same time, we are discarding all those observed variables which are not at all appropriate to have certain understanding of that factor structure. Now, EFA basically, as I have told you, and we have already said, is a variable reduction technique which identifies the number of latent constructs and underlying factor structure of a set of variables. It hypothesizes an underlying construct, a variable that cannot be measured directly, which we have already stated. It estimates factors which influence responses on the observed variable, the variables which are manifested, the variables on which we can actually collect data from the respondents. EFA allows us to describe and identify the number of latent constructs, although it will depend on how many factors are to be retained, how many extraction are to be done. So we can actually manipulate in those numbers also. Includes the unique factors, error due to unreliability in measurement. You will find in EFA, when we are synthesizing the entire process for assessment, or we are applying the entire statistical process, you will be seeing that certain amount of the factor, because in case of an EFA, the basic, you have probably already heard another term which is called the PCA, or the principal component analysis, which is almost following the same principle as of EFA. And the basic difference between PCA and EFA is, while PCA is more or less focusing on the variance structure, EFA is focusing more on the covariance nature of the entire model. So you will be finding certain error variants, which are actually terms, which are actually issues, which attributes for the unexplained part. So there is, to a certain extent, about the observed variables, which fails to describe the latent construct properly. So we assign a portion to the error variables, which can take up the responsibility to fulfill that unexplained part. Traditionally has been used to explore the possible underlying factor structure of a set of measured variables without imposing any preconceived. As I have said, that in EFA there is no preconceived structure. So we do not get a structure like the dependence, framework, like a set of a dependent variable and an independent variable, and then we can go the conventional kind of statistical analysis to understand the mutual relationship between those sets of variables. So there is no preconceived structure on the outcome. So what are the basic goals of EFA? It helps an investigator determine the number of latent constructs underlying a set of items. So if I want to dimensionalize the social phenomena, if I want to dimensionalize a social reality that is under study, if I want to dimensionalize a process, a behavioral process, if I want to dimensionalize a demographic process or psychographical process, I need to undertake the exploratory factor analysis, because I need to understand what are the underlying set of factors which can be used as a dimensional construct to explain that social phenomena or social reality or the behavioral pattern, etc. Secondly, to provide a means of explaining variation among the variables or the items. We normally call them the scale items, using a few newly created variables, which are called the components or the factors. In certain cases, they're also known as the dimensions, namely the condensing information. And to define the content or meaning of factors, namely the latent constructs. You need to, one of the major tasks which is involved in EFA is to nomenclate the extracted factors, because factors will be extracted as components. So in SPSS, the output that you get are component 1, component 2, up to component n, and n can be any figure, depending on the number of observed variables that you have brought into this entire equation. So one of the responsibilities of the researcher is to nomenclate or name those extracted factors, depending on the kind of observed variables that are loaded. So it's almost like a thematic analysis or content analysis of the observed variable. And depending on the theme, the common theme or homogeneity of theme, you tend to dimensionalize, you put a name for that extracted factor. So define the content or meaning of factors, or namely the latent constructs, with a particular name. Now, there are certain assumptions which underlie EFA. There are certain statistical assumptions, and then there are certain conceptual assumptions. The first assumption that the data has been collected, it should be at least an ordinal kind of a data. The data collected with the help of an interval scale or a ratio scale. There should be a random sampling. Although as a supervisor, what we are seeing, most of the scholars who are not in a position to go for a probabilistic kind of a sampling, they often take up this non-probabilistic kind of a sampling. And in most of the social science research, we find that convenience sampling is being taken up. And with the help of convenience sampling also, we have seen scholars are, implementing factor analysis on that, which is not desirable at all, because EFA demands that there should be randomization of sample selection. So random sampling or a systematic random sampling or stratified random sampling, whatever is possible, if there is a data set available with you, if you are working with a finite kind of a population where the population is known to you and you can extract the sample based on certain kind of database which you can access, it is always recommended that you go for a randomization of sampling. Relationship, one of the assumptions is relationship between the observed variable is linear. In case of EFA, it can be conceptualized in this way also. It is basically the transformation of a highly correlated set of observed variables into a set of linearly combined uncorrelated set of factors. So from a highly correlated set, we are supposed to dig out uncorrelated linear combination of factors or dimensions or constructs. But again, it depends. Although we tend to generalize on this particular concept, we can have certain differences in this perception also, because when the concept of rotation comes to play at a later stage, we will be dealing with the concept of rotation, the axis rotation that makes interpretation very easy about the construct and the observed variables. Or you can say the rotation which ensures unidimensionality. That means one observed variables must be loaded on one particular construct, and there should not be any cross loading. So we primarily focus on two different types of rotation. One is called orthogonal rotation. One is called an oblique rotation. Now, when we decide to adopt an orthogonal rotation, we basically allow the factors, the extracted factors or the latent constructs, to remain uncorrelated with each other. So the first concept that I said, that it's basically EFA is basically the transformation of a highly correlated set of observed variable into a linear combination of uncorrelated factors or uncorrelated construct. This is possible if we apply the orthogonal rotation that allows the factor to be differentiated and remain uncorrelated. But if we adopt oblique rotation, then we are deliberately allowing the extracted factors to get correlated with each other, to get into a kind of a relationship with each other. So our objectives must be different. When we are applying an orthogonal rotation, our objective is different. We want to see a very isolated kind of factor structure, the factors which will be highly differentiated from each other, so that we can dimensionalize the entire process. And on the other hand, if we choose an oblique kind of a rotation, we are trying to find out that unique set of factors which are highly correlated with each other, or there are interrelationship being shared by each of the extracted factors. So that depends on what kind of objective the scholar is having, and based on that, this rotational process may be applied or may be adopted for. The fourth assumption is, as far as the data set is concerned, it must follow a normal distribution. Also a bivariate normal distribution for each pair of observed variables, and the multivariate normality has to be assured also. So these are the 6 fundamental assumptions based on which we proceed for the EFA. So it has to be a scale data, more a ratio level kind of a measurement. At least ordinal data has to be at your disposal. There has to be application of probabilistic sampling. So the non-probabilistic sampling process, like a convenience sampling or judgmental sampling or purposive sampling or snowballing, etc. They are not very conducive for the application of the factor analysis. So random sampling techniques or probabilistic sampling techniques are apt for applying of the EFA. Relationship between observed variable is linear. We must have a kind of a normal distribution for each observed variable, a bivariate normal distribution for each pair of observed variables, and the multivariate normality has to be ensured. So these are the preliminary assumptions of statistical assumptions of the EFA. Now, for the EFA, there are certain conceptual assumptions also. So what are the conceptual assumptions? The first of the conceptual assumption is the selection of the variable. Now, the factor analysis is based on the basic assumption that there exists an underlying factor structure for the selected set of variables. So the researcher has to be convinced that I am searching for an underlying, and I'm pretty sure that there has to be an underlying factor structure for the set of observed variables. Now, the presence of a high correlation and subsequent interpretation actually do not guarantee relevance, even if it meets the statistical assumption. So therefore, it is the responsibility of the researcher to select the set of variables or items that are conceptually valid and appropriate to represent the underlying dimension. So, before setting up the EFA, your literature review and assessment of the variables is very important. If you cannot just simply select certain random elements or random variables, and if you tend to, throw it all in this particular statistical process, it will not hold good. So there has to be a theoretical, foundation for the EFA. So all the variables that you are selecting, it must lead, it must, signal, it must point to certain underlying factor. So that becomes very important. Conceptually, it has to be a valid set of observed variables that leads to a kind of unidentified factor. Okay, so that's very important. So that is where the researcher's role, the researcher's thought process, the researcher's involvement comes to play. Responsibility of the researcher to identify that set of those set of variables which are conceptually valid to explore whether there is an underlying factor structure behind it. And the second thing is about the sample homogeneity. The selected sample should be homogeneous with respect to the underlying factor structure. So if you are studying a particular social phenomena, or if you are studying a particular behavioral pattern, if you are studying a particular psychographical pattern, if you are studying a particular social reality, then there has to be your selection of the sample or the sample units within the sample frame. It should be homogeneous with respect to the underlying factor structure. So in your mind, you must be having some kind of an understanding about the hidden factor structure which you want to dig out from the set of observed variables. But there are certain limitations of the EFA also. The correlations, the basis for the factor analysis, it describes only relationship. So we cannot expect any kind of causality from that. So there cannot be any causal inference which can be drawn from that correlations alone. Because once you run the EFA, the correlational analysis is only a collateral. It will come out because we need to use that determinant value to assure that the data set that you are having, or the correlational matrix that you are having, it's not an identity matrix or a singular matrix. So that particular assumption has to be discarded. So it only assesses the kind of relationship that the variables share with each other, and does not say anything about the causality or the causal inferences. So that is one of the limitations. But we know one thing, that this interdependence technique, which we initially adopt to conduct an exploratory factor. Why it is called exploratory? Because we are exploring the factor structure. We are not sure about something which lies underneath the observed variable. So we are trying to explore. That's why it is exploration. But the second part where where it is leading, which is called the CFA, the confirmatory factor analysis, once we identify the factor structure, it has to be validated. So there has to be a construct validity, there has to be a dimensional validity, a discriminant validity, a nomological validity, etc. So all those validation issues comes to play. So if I want to convert an interdependence kind of a proposition into a dependence proposition, we start with the EFA, we get the underlying factor structure, we validate the underlying factor structure by adopting a CFA or by running a CFA, which is the confirmatory part of the factor analysis, and then transform it into a dependence, kind of a proposition by adopting an SEM, the structural equation modeling. So at the end, we can identify amongst all the extracted factors that which of the factors may be identified as a dependent factor, which factor or factors may be identified as an independent factor. So when we are proceeding for a SEM or a structural equation modeling, which is a dependence technique and which essentially follows a CFA, which essentially follows an EFA. So from a highly interdependence technique, we are proceeding towards a dependence kind of a technique. That particular transformation, that particular conversion is possible, but only after identifying the underlying factor structure. So exactly where the dependence technique is being applied, once your latent constructs or the factors or the dimensions are identified, then a scholar may be interested to know how these factors are related with each other. What is the strength of associationship between them, or are they sharing any kind of a causal relationship with each other? There comes the dependence technique. Okay, so it can be taken up also at a later stage. The reliability of the measurement instrument, that is one of the limitation. Avoid an instrument with a very low reliability. Normally, when we are, because in case of a EFA, what we are getting as an output is a measurement scale. Okay, so the validation of the measurement scale is done by the CFA. So the internal scale reliability is measured with the help of an alpha value. Okay, so we will see that also. It is normally called a Cronbach's alpha. So if the reliability score is pretty low, normally we do not, consider a particular measurement model as a very robust whose Cronbach's alpha value is less than 0.85. Although you will find scientific references, many times they have been cited, that any Cronbach's alpha which is more than 0.70 is considered to be a valid one. But under normal circumstances, as researchers, we do not recommend a Cronbach's alpha value of less than 0.85. So higher the Cronbach's alpha, more reliable is your measurement instrument. So the reliability of the measurement instrument is often under question if the reliability score is very low, and we need to discard or avoid such kind of instruments with a very low reliability score. Then the sample size, larger the sample size, larger will be the correlation. Now, there is a rule of thumb. Often the scholars come out with this particular question, that if I want to conduct an EFA, what will be the minimum sample size? And now there is a rule of thumb for this. What is it? So if you are having, say, 10 observed variables, so it's the number of scale item, if it is 10, then the minimum sample size that you have to take into consideration is 5 times the number of observed variables. So the minimum sample size is 10, but we recommend the minimum sample size should be 10 times the number of observed variables. So if you have 10 observed variables, the minimum sample size should range, the sample size should range between 50 and 100. Preferably, it should go closer to the 100. Okay. Now, since some subjects may not answer every item, a larger sample is desirable, because although there is a technique of imputation of missing data, and with the help of the SPSS package, you will be able to impute the missing data. It is not very scientific, because it creates a mean and then it replaces the mean value with that particular spot which is left unresponded. So to be on the safer side, you should go for at least a decent kind. You should have a decent kind of a buffer, so that all those responses with missing values can be discarded in its very first place. So suppose you are having 30 items or 30 scale items or 30 observed variables. So the minimum number of sample size you will be requiring as per the theoretical concept is 150, 5 times the number of observed variables, but it is recommended that you should go for 300, if not 300, very close to 200 and 250, so that you have a good buffer to discard all those responses with a lot of missing values. Okay, so if you have, say, 60 or 70 responses which are having 1 or 2 or more than that missing values, it will not come down below 150 even if you discard them. So larger the sample size, better will be, in case of factor analysis, when we will be using the SPSS to conduct that particular analysis, you will find one particular test result becomes very important, which is called the Kmos test or the Kaiser-Meyer-Olkin test. Basically, the Kaiser-Meyer-Olkin or the KMO is a measure of sample adequacy. So normally a very high figure or a very high value of Kaiser-Meyer-Olkin, it satisfies the required number of samples. So sample adequacy may be checked with the help of this particular test. A very low value of KMO means that the data set that you are having is not amenable to the EFA technique. So you need to discard that. Then the sample selection normally, in case of EFA, what we see in practicality is it's a representative of a population and do not pool the entire population. The variables could be sample specific, namely a unique quality possessed by a group does not, it generalize to the entire population. And it's very difficult to ensure the normality of the data. So often we have seen normal distribution of data also. So these are the few limitations of EFA, but considering all these limitations, EFA is a very potent technique with the help of which we can actually identify the factors, we can identify the dimensions from a given set of observed variables. And it is very important multivariate technique that is used pretty widely, particularly, when you are developing a new construct, when you are developing a new scale, the EFA technique becomes very important. Okay. Now, one of the major things in EFA is the factor extraction. Okay, factor analysis, we will see the criteria for extracting the factors. So factor analysis actually seeks to discover the common factors. Okay, so the technique for extracting factors, it attempts to take out as much as common variance as possible in the first factor. So the subsequent factors, let me just repeat this. The technique for extracting factors, it attempts to take out as much common variance as possible from the first factor itself. So the subsequent factors are, in turn, intended to account for the maximum amount of the remaining common variance until, hopefully, no common variance remains. So the direct extraction methods obtain the factor matrix directly from the correlation matrix by application of specified mathematical models. Most factor analysis agree that direct solutions are not sufficient. Most factor analysis agree that direct solutions are not sufficient. So the adjustment of the frames of reference by rotation methods, I told about that, orthogonal rotation and the oblique rotation, improves the interpretation of factor loadings by reducing some of the ambiguities which accompany the preliminary analysis. So the process of manipulating the reference axis is known as the rotation. So if anybody asks or anybody wants to understand what is the conceptual thing behind this rotation issue, the process of manipulating the reference axis is called the rotation. So we will make a graphical representation of how the rotation takes place and what exactly is meant by rotation and why rotation is required. That we will see in a minute. Now, what are the criteria for extracting factors? There are specifically 4 criteria. The first one is called the Kaiser's criterion. Now, Kaiser's criterion, which was suggested by Gutmann, and it was adopted by Kaiser, considers that factors with an eigenvalue greater than 1 as a common factor. It was cited by Nunnally and Bernstein in 1978. So let me just repeat it. In case of a Kaiser's criterion was adopted by Kaiser, and which was suggested by Gutmann. It considers factors with an eigenvalue greater than 1 as common factors. Now, what is an eigenvalue? It represents the total variance explained by each factor. Okay, so eigenvalue is one of the parameters. There are a few parameters with the help of which the robustness of an EFA output is measured. One of the parameters is the eigenvalue. The second parameter is the communality. The third parameter is the total variance extracted. So all these are criteria for extraction of the factors. So the first criteria is the Kreiser's criterion based on the eigenvalue. The second one is the Cattell's Scree test. Okay. Now, Scree is basically a graphical representation. We will see what a Scree plot looks like. But there is a very interesting, anecdote about this Scree test. It is called the Cattell's Scree test. Now, the name is based on an analogy between the debris which is collected, which is known as scree, which is collected at the bottom of a hill after the landslide. So, what is a scree? A scree is a collection of debris and rubbles, which is collected at the foothills after a landslide. And if we apply it into the EFA technique, it is the relatively meaningless factors that result from the over extraction of the factors. Okay. On a Scree plot, because each factor explains less variance than the preceding factors, an imaginary line connecting the markers for successive factors generally runs from the top left of the graph to the bottom. So there is a cutoff value. Normally, in case of an EFA, we call it in the Scree plotting, we will find an elbow. There is a hinge. Okay. Now, the hinge is very important because above the hinge or above this particular elbow lies those factors for which the variance is maximized, and below that, a very small degree of variance is explained. So the retention of the factors, or the extraction of the factors and the subsequent retention of the factors takes place whatever factor is above this hinge line or above this elbow. So when we are setting the eigenvalue greater than equal to 1, normally we do not set it at equal to 1. It's always greater than 1. So the elbow starts at that particular level where the eigenvalue is 1, that particular hinge. So anything over 1, all the extracted factors are retained because they are instrumental in maximizing the variance. So the explanation of the model in terms of variance structure is done by those extracted factors which are residing above this particular elbow or above this particular threshold value of eigen. And below this, all such things are discarded. All such factors are discarded or are not taken in the particular model. So this is the Cattell's Scree test, which is a graphical plotting which allows us to visualize which are the factors that are retained and which are the factors that are discarded. Then the proportion of variance. The proportion of variance accounted for keeps a factor if it accounts for a predetermined amount of variance, say namely 5% or 10%. Then interpretability criteria. There are few things that helps in interpretation of extraction of the factors. So that can be explained when we take up the SPSS process also. Now, how a EFA model or a EFA equation looks like. We can represent the EFA model with this simple equation: y is equal to x beta plus e, where y is the matrix of the measured variables, that means matrix of the observed variables. X is the matrix of common factors which are extracted. Beta is the matrix of weights. Weights means all the factor loadings. Factor loadings means all the correlational values between the observed variables and the extracted factors. And E is the matrix of unique factors or the error variation. So this is the underlying model for EFA. Y is equal to x beta plus E. Now, what are the EFA steps that is normally followed? There is an initial extraction. There is a determination of the number of factors to be retained, and we go for Scree test, we go for proportion of variance, etc., interpretability, etc. Then we go for a rotation or a transformation. We go for interpretation of a solution. So there are essentially 4 steps. One is the initial extraction of the factor. Even there can be an unrotated factor extraction also. Now, to check the unidimensionality, we go for the rotation. The second step is to determine the number of factors to be retained, that I have already discussed, that anything over the hinge or the elbow or anything greater than 1 in the eigenvalue should be retained in the model, and the rest will be discarded. So the rest is basically the screen, the lower part of the graph. And the third thing is the rotation, which is very important, and we need to understand and then interpret the solution. Now, I do not just go through this one. Yeah, the concept of rotation, which is very important, one of the most important things in the EFA. An important difference between the rotation, that means we got two different kind of rotation. One is oblique one and one is an orthogonal rotation. So rotations that allow for correlations are called oblique rotation, and rotations that assume that the factors shall remain uncorrelated with each other. So there is a differentiating value, or there are certain differentiating issues between the extracted factors, then we go for the orthogonal rotation. So at the very beginning, I made it clear that it is the objective of the researcher. The researcher has to decide whether to maintain a set of highly correlated factors or a set of highly uncorrelated factors. Okay, so based on that particular objective, the researcher may adopt oblique rotation or an orthogonal rotation. Now, in case of an orthogonal rotation, normally we use the maximization of the variance kind of rotation, which is called the varimax rotation. So it maximizes variance of squared loadings across the variables. So sum over factor. What is the goal of this particular rotation? If we adopt the varimax rotation, the goal is the simplicity of the interpretation of the factors. Okay, so it maximizes variance of squared loadings across all the variables, across all the observed variables. But there is another one which is called the Quartimax. It's also a kind of an orthogonal rotation, which maximizes the variance of squared loadings across the factors, not across the variables. So it is the sum over variables. What is the goal of a Quartimax kind of a rotation? The simplicity of interpretation of the variables, not the factors. See, in normal cases, we want to interpret the factors because we know the basic objective of the EFA for most of the scholars, for most of the researchers, is to understand the factor structure which is hidden, which is unmanifested. So the simplicity of interpretation of the factors should be the objective or should be the goal. And as a result of which, in most of the cases, when we adopt orthogonality, we normally opt for the varimax rotation. Now, let us see graphically how this rotation or this unidimensionality takes place. Now, you see, this is an orthogonal position. Now, when we speak of an orthogonal position, the axis actually cuts one another at a 90-degree angle. Now, you see, if we consider this y-axis and x-axis, and if we consider say the variable plotting over here, see variable number 1, variable number 2, variable number 3, these have been plotted. See, this is factor 2, this y-axis, it is representing factor 2, and this axis is representing factor 1. Actually, it should be UF2, unrotated factor 2, and this is unrotated factor 1. This is exactly before the rotation takes place, okay? Now, what is the difficulty associated with it? Okay, say, for example, if I, unfortunately, the calibration is not done, say this is 0.5, this is 0.7, this is 0.8, this is also 0.5, this is 0.7, this is 0.8. And on the left-hand side, it will be the negative values, minus 0.5, minus 0.7, minus 0.8, or something like that. So similarly, in case of this particular axis also at the bottom level. Now you see this variable 1, if I consider this as 0.5 and this is 0.7, so this variable 1 has been loaded on unrotated factor 2 or at 0.7. So the correlational value between this observed variable 1 and latent construct 2, that means factor 2, is 0.7. Okay, this is as far as factor 2 is concerned. Now this variable 1 is also loaded on factor 1. This is unrotated factor 1 at this particular place. This is 0.5. So this is 0.7 for unrotated factor 2. This is 0.5 at unrotated factor 1. Correlational value 0.7 and 0.5. Now, it is very hard and difficult for the scholar to discard either one of these values, because 0.5 is also significant value as far as the correlational values are concerned. 0.7 definitely is a high correlational value. So which value is to be discarded? So the researcher is in a dilemma that where to assign this particular, observed variable. Should it be assigned to factor 2 or should it be assigned to factor 1? So we are facing an issue of unidimensionality. Unidimensionality says that one observed variable should be loaded onto a one particular factor. It should be assigned to a one particular factor. To ensure unidimensionality, we need to tilt the axis. We need to go for a rotation to make the solution more interpretable and easy. Here, the scholar is in a dilemma because both the factors are demanding their share of the observed variable. You see the second graphical representation over here. This particular arrow mark is showing how this orthogonal rotation is taking place based on the algorithm that is used up by the Spss. So it tilts the axis at a 90 degrees. So the 90 degree, this orthogonality is maintained. That means the axis cuts each other at a 90 degree angle. Now you see, since the axis is tilted, what has happened over here? This is the rotated factor 2. This is the rotated factor 1. Okay. Now, how it has changed? Now you see variable 1. It is loaded in rotated factor 2 at somewhere near 0.7, 0.75. But when it comes to rotated factor 2, it is very negligible. It's almost it has almost over here, say -0.1 or something like that. Now the researcher can easily say that this observed variable can be assigned to this rotated factor 2, not to rotated factor 1. Okay, because the rotated factor 1 score is significantly lesser. The correlational score is -0.01 probably compared to the correlational score with rotated factor 2, which is close to 0.75. So, so when we are going for a rotation, we are making things interpretable. We ensuring unidimensionality so that one particular observed variable can be assigned to one particular factor. Otherwise, there will be, cross loadings and there will be difficult in interpretation. So that's basically is the essence of the rotation. If we go for oblique rotation, oblique rotation, first of all, it doesn't stick with this 90 degree cut. So it can be at various angles. It can be a 30 degree angle or 45 degree angle, whatever it is. And it allows the extracted factors to be highly correlated with each other. Now, how that high correlation is established? Highly correlation can be established if there is no issue of unidimensionality. So one particular observed variable can be loaded, cross-loaded or simultaneously loaded into extracted factors. So there has to be, correlation between those two extracted factors. So if it is an orthogonal rotation, a researcher deliberately opts for differentiating factor 1 from factor 2, from factor 3, from factor 4 up to factor n. But if a researcher is opting for oblique rotation, he or she wants to establish a kind of relationship between the extracted factor 1 with extracted factor 2 with extracted factor 3 up to extracted factor 4 up to extracted factor n. So hopefully this rotation process is clear. So once we complete this process of EFA, we proceed for the validation of this particular measurement construct with the help of a confirmatory factor analysis, which we will be taking up in the second session. And all the validity issues like the convergent validity and the discriminant validity and the nomological validity, etc., can be established. Okay. So this is in brief how the factor analysis takes place. What is the fundamental posit of factor analysis? So now we can take up a case study, and with the help of a data set, we can actually use the SPSS for testing one particular data set. Now, this is the case study or the example which we will be considering. What this case says that consider, this is a hypothetical case. Consider a construction company, say for example, ABC Builders, that is planning to build an apartment complex near a university. And suppose the company is interested in identifying the perception of the university faculties regarding the value consciousness and the price consciousness and the purchase decision involvement and the sell proneness that would help the company to construct and design apartments according to the target people. So the company hired a market research firm to determine how these four major response dimensions the faculty is concerned about before buying an apartment. So the research firm identified the scale to measure these four constructs using some existing literature in price consciousness. So they have used 3 items for price consciousness. They used the 5-point Likert scale to generate the response. For value consciousness, 3-item scale has been used. For sale proneness, 2-item, and for PDI, 4 items. So how many observed variables are there? 3 plus 3 plus 2 plus 4. So it's 6, 8, 12. So 12 observed variables. And how many latent construct? One is price consciousness, one is value consciousness. The next one is the sale proneness, and the fourth one is a PDI. So they want to check this 4 latent constructs. Okay. So the firm surveyed 98 randomly selected respondents or faculty members using different scales to determine the perception of the faculties with regard to the PDI, price, value consciousness, and self-proneness. Now you see, this 98 number is justified over here because you have 12, observed variables. So the minimum sample size that was required was 12 into 5, that is 60. And they have kept a buffer of 38. So if you have certain issues regarding missing data, you can actually discard some of those responses, and you can have a very neat and purified set of data that doesn't have any missing values. Okay. Anyway, they have collected 98 responses from the faculty members. So the sample size is 98. Now let us just check on the data set. Okay, so this is the data view. As you can see that there are 12 variables. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now if you go to the variable view over here, I have not just named the way, I have just allowed it to stay like that only. Now variable 1, variable 2, variable 3, 4, 5, 6, 7, but I have changed the label. Okay, so if you see these labels, what exactly this variable denotes. Okay, so for variable 1, selecting from many types and brands of this product. Product means the apartments, because ABC is a builder who builds apartments available in the market. Would you say that that means what is your opinion regarding selection from many types of products and brands which are available from the market? So variable 2 deals with this particular query. Do you think that the various types of brands of this product available in the market are all very alike or all are very different? So they have used a 5-point Likert scale to generate this particular response. Variable 3, it deals with a question: how important would it be to you to make a right choice of this product from the ABC builders? So similarly, we have 12 questions for representing these 12 variables. Okay, so over here, what we need to do is this measure, all are by default nominal, so we can change it to scale level because we have used the interval scale to collect all these responses. So just change it to the scale level. And one more important thing at the last column that you can see is the role of these variables. See, in case of factor analysis, since this is an interdependence technique and we do not have a set of dependent variables and we do not have a set of independent variables, we treat all the variables as an input variable. So otherwise, what would have happened, had there been a dependence kind of a framework, there should have been certain targeted variables. Okay, so all these variables are basically inputs. We require each and every variable as an input variable to conduct this, exploratory factor analysis. So all these variables are to be marked as input. So there is no target variable. Target variable only comes to play when the interdependence format is changed into a dependence format. So you have predictions and the strength of associationship, correlation, etc. So let us go to the data view once more. And now we will go for the analysis. Okay, now before conducting the analysis, primary analysis, we want to check the reliability issues, the scale reliability or the internal reliability of the scale. So we said that one of the values which is very important for us for scale reliability is the Cronbach's alpha. Okay, so let us see the alpha value. So you go to analyze, and then you go to this scale, okay, and you go to the first option, which is called the reliability analysis, and you will find by default this alpha is taken. So there can be other reliability coefficient like split up is there, Gutman is there. They are used for other tests. So we will be sticking with alpha. And we will be selecting all these variables, and you will drag it in the this particular box, which is called the item box or the variable box. You just shift it, select it, use this arrow, it will be shifted. So no further statistical, adjustment has to be made. Okay, we just want to see the alpha value. We just want to test. Okay, so just click OK. See, the alpha value is 0.838. Normally, as I have told you, that theoretically speaking, any alpha value which is greater than 0.7 is accepted as a mark of reliability or the internal reliability of a scale. But as a researcher, as a supervisor, I do not, or we do not recommend any value which is lesser than 0.85. We do not recommend. But here, the Cronbach's alpha value is 0.838. It's close to 0.85, say, for example, for this demonstration purpose. Let us accept that this internal reliability of the scale has been achieved. Okay, so this is the first set of test that we are supposed to take up to check the internal reliability. And now we just want to proceed for the factor analysis. So again, we go to this particular command called analyze, and in this particular drop down menu or pull down menu, you will find one particular menu, one particular tab which says dimension reduction. It is the the thematic representation of what factor analysis actually does. Okay, dimension reduction, if we just hover on this particular tab, you will find another set of drop down menu, and the first one is called the factor. So we are just clicking on this. See, already the variables are over here. So under normal circumstances, what will happen when you will be doing it for the first time, your variables will appear here. Okay, all the variables. So what you need to do is to go for selection. You select one and you can go for Control A. So once you click Control A, all the variables will be selected. You just pull all the variable on this variable window. So you use the arrow after selecting all the variables, just click this arrow and all the variables will be pulled into this variable window. Okay. Now you set all these criteria. The first criteria is allotment of the descriptive stats. The second criteria is the factor extraction process. The third criteria deals with the rotation. The fourth one is about computation of the scores. And the fifth one is about the options. So let us see the first criteria, which is called the descriptive. See, we need to understand the univariate descriptives and the initial solution. This is very important. The determinant, always stick on this. This is very important, the Kmos and Bartlett's test of sphericity. So we need to have that also. So continue. So what we have ticked over here, you can check on the coefficient. You can check on the significance levels also. Some researcher may go for anti-image matrix. Anti-image, which basically it will be a mirror image of what correlational matrix looks like. Absolutely mirror image. So some interpretations can be received from there, but since you are dealing with correlational matrix, you do not have to pull down anti-image. So Kmos and Bartlett, determinant, initial solution, coefficient, univariate descriptive. These are more than enough. So continue. Then the extraction. You see, you want to see the scree plot. We have discussed a lot about the scree plot. We need to see the hinge, the elbow. And we also want to see the unrotated factor solution. Okay, the unrotated factor solution, we need to see the correlation matrix. And this is very important in terms of extraction. When we are extracting the factors, we are putting the eigenvalues which are greater than 1. We are considering. So this particular parameter is directly linked with the graphical output, which is the scree plot. In the scree plot, you will find that the elbow or the hinge that we are actually talking about will just start from that eigenvalue of 1. Okay, so continue. Then comes the rotation. Obviously, we will go for orthogonal rotation with maximization of a variance. So we will go for varimax rotation. As far as the display is concerned, I want to see the rotated solution. Some of you may be interested to go for the graphical representation. So you can click in here also, that will load the plots for you. Continue. Then the scores, you need not do anything with this particular thing at this particular moment. Options. Now this is interesting. You see, sorted by size, and there is another option which is called suppress the small coefficient. Okay, you can actually specify. Say if I want a very accurate model and a very robust model, I can actually make this value 0.60. So anything below 60 will not be loaded. But for the time being, I am not interested about this. So I am unchecking this. Okay. So let me allow all the matrix, the full matrix to be shown. So continue. So we have finished complying with the descriptive, with the extraction process, with the rotation, with the scores, which we didn't do anything with the score, and the option. Okay, so we simply click OK. Fine, so the calculations, the computations have been done. These are the descriptive statistics. So we have the mean standard deviation, the n, or the sample size is 98. So you see, this is the first check that will assure you that there is no missing value. So there is no discarding of any cases. So all the 98 cases have been pulled in. Now, this is the correlational matrix, okay, with a determinant value of 0.007. We will interpret everything because this determinant value has to be reported. When you will be writing a journal paper or when you will be writing a thesis, there are certain things for factor analysis that are very important to be reported, okay? So this is the Kmos and the Bartlett's test, which has to be reported also. These are the communalities. Communalities is the amount of variance available that shares with all the other variables being concerned. This is also the proportion of variance explained by the common factors. So all these communalities are here. And then the total variance explained, we are seeing that the number of rotated factors that has been extracted is 4, because these 4 factors are explaining a total variance of 71.493%. Okay, so this rotation sums of squared loadings, it is signifying that there are 4 major factors that has been extracted through this EFA process, which is explaining a total variance of 71.493%. Now this is the scree plot. Now you see on the vertical dimension, the eigenvalues are plotted. So you can easily remember what we did in the factor extraction. We have stated that all the factors to be retained in the solution whose eigenvalues are greater than 1. So this is the threshold limit. This is 1. So over this 1, this is actually the elbow or the hinge, okay, below which you will have the scree or the rubbles. Okay, we gave that analogy of a landslide in a hill. So all the rubbles, all the discarded items, all the unused or you can say useless things, they are deposited at the foothills. Okay, so just above this 1 value, that means eigenvalue 1, how many factors are there? 1, 2, 3, and 4. So graphically, it is also established that we have a 4-factor solution for this EFA process. Okay, 4-factor structure. This is the component matrix. Now you will see what is the difficulty. Say, for example, this is component matrix. What does it signify? This is unrotated. That means this particular component matrix is basically before the rotation. And you will be interested to know this particular communality that we have got earlier. The communality extracted for the first variable is 0.494. Now you will be very interested to know that from where this particular figure is coming, this 0.494, okay, or where this particular figure 0.825 for the second variable, the communality is 0.825. From where this communality 0.745 correspond to the third variable is coming. See, these extraction or the communality figures are coming from the summation of the squared components. Okay, so if I add up square of this plus this, square of this plus square of this plus square of this, this will be the communality for the first variable. Then if I come down to the second one, square of this, square of this, square of this, square of this, that means summation of the square of the components, then we will get the communality of the second variable. So if you want to cross-check, use a calculator and do that, you will get all the values of these extracted communalities based on the component matrix, which is unrotated, remember. Okay, now we said a lot of things about the rotation, and we said that rotation basically ensures unidimensionality. Otherwise, a particular scholar may face a lot of problem. The basic problem is for a scholar is, if there is, there are 4 factors, and if you find that a variable is loaded significantly in 2 factors, then it will be very difficult for the for that particular scholar to assign. Now you see in practical what has happened. This is a variable which says I am not willing to go to extra effort to find lower prices. Okay, so this is a variable against which this is a variable which is correlated with factor 1 with a value of 0.617. This is a variable which is correlated with factor 3 with 0.597. So what is the difference between 0.617 and 0.597? It's virtually nothing. And both these correlations are quite significant. So as a scholar, if I am a scholar, then which one is to be retained? Should I retain this solution? That means I am assigning factor this variable, this particular variable under factor 1 or component 1, or should I assign this particular variable to factor 3? Both of them. So it's very difficult for me to discard. Now you can actually correlate what we theoretically did a few minutes back. This is a very difficult thing. See, for example, over here, this particular variable loaded in factor 1 or component 1 with a value of 0.412. This is a correlational value. 0.412 is quite significant. You cannot discard it. And then in factor 2, it's 0.763. It is also very strong. The correlational construct is also very strong. You cannot discard it. You come to the next variable, 0.519, 0.672. Very difficult to discard 1, to negate 1. So it is uninterpretable in nature. And it will pose a lot of difficulties, because once you have this kind of a structure, this kind of a factor structure, and you have applied for orthogonal rotation, and you have not applied, you have not applied for rotation, and you have retained this particular factor structure, then there will be several issues after design, after you conceptualize this factor structure and move on for further analysis. So for maintaining unidimensionality, we need to ensure that one particular factor is loaded in one particular observed variable is loaded in one particular factor only. So there will be no kind of a cross loading. In when we will deal with CFA, you will find that there can be two models. One is called a congeneric model, one is called a non-congeneric model. Normally, in a non-congeneric model, there are a lot of cross-loading, making that entire model very weak, very feeble. Okay, a lot of questions can be taken up with regard to those models. Okay, so again, we are going to analyze. Okay, dimension reduction. Go to factor. Go to rotation. We have gone for Varimax rotation, so we'll leave it like that. But come to this option, okay? Suppress all the small coefficient, okay? Now, I want to suppress all the coefficients which are below, say, 70. Fine. Continue. Okay. Now, you come to the rotated component. So let us see the rotated component matrix. This is the rotated component matrix. Now you see that there is a clear-cut indication of specific variables loading onto specific factors. So 1, 2, 3, the first three variables are loaded on factor 1, so there is no cross-loading. The variable 5, 6, 7, they are loaded on component 2, so there are no cross-loading issues. This is 8, 9, 10 probably loaded in factor 3 or component 3, and 10, 11, 12 in factor 4 or component 4. So this is now clear. Okay. Now it is much more interpretable. Fine. Now we also discussed about one thing, that once the factors are extracted, or once the component is extracted, these are the components, or in other words, we call them as factors. Once the factors are extracted, it is the responsibility of the scholar to assign certain names to these factors being extracted. Okay. And how these names will be assigned? These names will be assigned by going through the theme of these variables. Okay. We want to check, as a scholar, we need to check whether these three variables are highly correlated, not in the statistical sense, but whether they are actually saying the same thing, or they are mutually thematically very close to each other. And based on the overall theme that these three variables are discussing or have captured, we want to use that thematic representation as a nomenclature for this particular component, or for this particular factor. So how the factor namings are to be accomplished? The factor names or the construct name or the component names or the nomenclature for the components are to be done based on the thematic similarity shared by the variables who have shared significant correlationship with an extracted factor. Okay, so that is the responsibility of the scholar to read these variables very carefully and try to find out the thematic connect between these three variables for this factor 1 nomenclature, thematic connect between these three variables for factor 2 nomenclature, so on and so forth. Okay. Now we come to another important criteria, which is the total variance explained over here. Okay. We have seen that the total variance explained by the rotation sums of squared law. We have already understood that there are 4 factors to be retained in this particular solution. The graphical representation also shows that anything below the eigenvalue of anything above the eigenvalue of 1, only 4 factors have been extracted. Over here also the rotated solution, it shows that 1, 2, 3, 4 factors have been extracted. So in the total variance explained, you see 71.493. That's a quite sizable portion of variance being explained. So we use that varimax rotation, maximization of variance. So these 4 factors have gone to the extent of explaining 71.493% of variance in this particular model, which is significantly high. Okay. So this particular 4-factor solution to be retained, so you need to report this total variance explained also. So what are the things you need to report when you are writing factor analysis, interpretation or the factor analysis result? The first one that we need to report is the determinant. Here the determinant value is 0.007. So in this example, we have got this value of 0.007. It is neither an exact 0 nor an exact 1, which is greater than the cutoff value of 0.00001. Okay, so therefore we can just conclude that the correlation matrix is neither an identity matrix nor a singular matrix. Okay, so this value confirms that the assumptions that there are sufficient interrelationships among the study items or amongst the observed variable. So had this been a singular matrix or an identity matrix, this particular data set would not be a good data set to conduct a factor analysis. So you should not proceed further. So it is not a direct 0 or an absolute 0 nor an absolute 1. So it ranges between 0 and 1, and it is well above the cutoff value of 0.00001. The next that you need to report is the KMO, the Kaiser-Meyer-Olkin test, the Bartlett's test of sphericity. This particular table is giving you that result. You see the KMO value is 80.806 over here, and Bartlett's test, it gives you the chi-square value. The approximate chi-square value is 452.251 with a 66 degrees of freedom with a significance which is quite acceptable. Now, you see what Bartlett's test of sphericity does. The Bartlett's test of sphericity, it tests the null hypothesis that the correlation matrix is an identity matrix, that there is no relationship between items, and follows the chi-square distribution. So larger the value of the Bartlett's test indicates a greater likelihood the correlation matrix is not an identity matrix, and the null hypothesis can be rejected very easily. So in this case, you can see that the approximate chi-square value is 452.251 is significant. That is a significance value of less than 0.05. So this what does this mean? This means that we may reject the null hypothesis that our correlation matrix is an identity matrix, and we'll conclude that the variables are correlated highly enough to provide a reasonable basis to conduct the factor analysis. So whether the data set is amenable to conduct a factor analysis, and should we proceed with the factor analysis, it can be tested from this particular Bartlett's parameters. And the next is the KMO. As I have already told you that the KMO is basically a test of measuring the sample adequacy. The KMO measure should be greater than 0.70. Okay, if it is lesser than 0.70, then there is a question mark about the sample adequacy. In this case, you see, the KMO value is 0.806, so there is no issue with regard to sample. In any case, we had only 12 observed variables and we collected 98 samples, and all the samples were retained in for the analysis process. So not a single response was discarded simply because of missing value. So 12 and 98, it is almost, almost you can say 8 times the number of observed values. So it is well within, the number of sample which is desired. So all these 3 measures, one is the determinant, the second one is the Bartlett's test, and the KMO. It shows the evidence that there are good interrelationship between the study items, that means the observed variables and measures. Therefore, we can go for factor extraction, because the next set that you have to report is the extraction of factors. So we go for the these days we do not report the communalities, not required, but you need to just mention this total variance explained. That means how many factors, extracted factors, have explained what amount of variance. So you need to report that also, the percentage of variance being explained by the extracted factors. For a journal paper, you need not put the graphical representation, okay? You need not give the scree plot. But when you are writing a PhD thesis, you can report the communalities, you can report each and every, starting from the descriptive stat, everything, okay? But for a journal paper, it's not required because your total variance explained by the extracted factors, that is more than enough. And then you have to report for the rotated component matrix, because this will allow you. But when you are representing the rotated component matrix, make sure when you are inserting this table in your journal paper or in your thesis, make sure the nomenclatures or the naming of the factors are done, okay? Because that is very important. The nomenclatures has to be done, okay, before you report it. Fine. And the last thing that we do nowadays for one of the most important reporting is the common method bias, okay, or the CMB. The common method bias simply states that, or simply assures or confirms that a single factor is not responsible for the maximum variance, okay? So your factor structure is not dependent on a single factor, and it necessarily not, explains the maximum variance in that particular model. So the common, this CMB, the common method variance, this always deals about whether the factor structure is highly skewed towards a single factor extraction, which is not at all representation of a robust model. So that thing has to be established. And here you can see that it's not a single factor, but a set of 4 factors that is explaining 71.493% of variance in the model. That is quite high. So these are the things that are to be reported for in the factor analysis. So the first thing we need to report is the reliability, the Cronbach's value, alpha value for the scale reliability. The second thing that you may report is the correlational determinant, which actually proves, or which actually should ideally prove that the correlation matrix is not an identity or a singular matrix, which is not very suitable, or which is not very friendly to conduct factor analysis. Then the Bartlett's test, it basically rejects the null hypothesis that this correlational matrix is a singular matrix. So higher the chi-square value, better you will have the chance to reject the null hypothesis. The KMO value, it should be greater than 0.8, at least greater than 0.7 to be very assured about, statistically, assured about that you have a adequate number of sample to conduct the factor analysis. And then you move for the total variance explain and the solution, the factor structure solution, that is the rotated factor structure. Okay. So the rotated component matrix with all the nomenclature and the common method variance. Okay. These are the few things you need to mandatorily mention when you are reporting for the EFA. So when you are writing for a paper or for a journal, don't go for graphical plots, because if we carry forward this particular analysis to say confirmatory kind of a factor analysis, you will find that a lot of graphical representations have to be done there, because the measurement model, if you take it one step further, to develop a structural equation model or the structural model, which is a dependence kind of a framework, there also you have to incorporate the graphical structure. So it's not required. The graphical structures are not required. But when you are writing a doctoral thesis, I think all the reports are to be appended. So that is all about EFA. But before I conclude, I want to show you one more thing. No, when we are using SPSS, most of us are using SPSS. SPSS, as you all know, is basically what to say? It's a proprietary software, isn't it? You have to purchase it, and it's very costly. Okay. As a result of which, although this is a workshop of SPSS, but for those scholars who may face certain difficulty in accessing SPSS, there is an alternative open and free source software which is called PSPP, which is available over the internet. You can download this. You can just install it in your machine. It will do all the things that SPSS does. Okay, the full form is PSPP. You can go for Google search. You can just download and install it. The appearance is not that glamorous like SPSS. SPSS is a very colorful kind of an interface. PSPP is all black and white. But if you compare the interfaces item-wise or tab-wise, you will find there is hardly any difference. And you can do each and every operation that can be done on the SPSS platform. And it's almost an anagram as far as the name is concerned. So PSPP, this is open and free source. So you can download and use it for those scholars who might face certain difficulty in accessing SPSS. So this is number one. And number two, I want to show you another kind of SPSS. Probably you have already heard about it, which is called, there is another version of SPSS, which is called SPSS modular function. Okay. Not the normal SPSS that we use, the IBM SPSS that we use. It is also a proprietary software of IBM. But over there, they are using a modular function, much more advanced in nature. Okay, so I will just show you that particular functionality once, so that you can understand. In most of the industries, particularly the corporate houses, they are using it for advanced predictive modeling. Okay. For better model development, machine learning, etc. So this, I will show you how to conduct a PCA exploratory factor analysis on this platform also. Okay, so this is the SPSS modular function. So the IBM SPSS modular is slightly different from that of the IBM SPSS. Now, how it is different? Actually, the functionality, as you will be seeing, see, the interface is totally different. There are two tabs over here at a upper side horizontal navigational tab and the lower side at a bottom navigational tab, and all the operational elements are stacked up here. So you have the sources from you have a sources tab with the help of which we can import data. You have a record option, you have a field operation, you have a graphical output option, you have a modeling function, and you can see how many different types of modeling can be done. You can go for very advanced kind of analytical process like SVM, the support vector machine, and the artificial neural networks, KNN, the K nearest neighbor analysis, K-means clustering, Bayesian analysis, all those things, okay, logistic regression analysis. Then you have an output tab, and you can also make an R output. So those people who are very flamboyant with using R or Python, they can get certain output which is compatible with the R interface or R Studio, and you can export it in almost all formats, okay. And then you have the IBM SPSS statistics. So with the normal statistical platform, IBM SPSS statistics, you can actually integrate this, okay. Now, one important part or operational part of this particular SPSS platform or this modular platform is this is done on the basis of a node-to-node connect. So you have to build up a node framework, okay. So that node framework has to be developed before it is given a command to run and execute a particular function. So we need to deal with a particular issue called EFA or exploratory factor analysis, and let's just have a quick look that how this modular platform also can do this. So first I am just going to these sources because I need to pull down the data first, okay. So over here you see it is written over here, the cursor is hovering on this particular tab. It's called the statistics file. So I'm just double clicking it. So the first node appears on the screen. So as I have told you, it will be an interconnection of nodes, okay. So the statistics file is double clicked because now we want to import the data. So I'm just browsing it. I have kept my data in the desktop in a folder. Okay, so this is the EFA data set. Open. It's apply. Okay, so this is the data have been imported, but I cannot see the data directly from this tab. Okay, so I have to use another tab to see this particular data. Okay, I need to bring over here a tabular kind of a tab which will help me to visualize that data. So you see under this output particular tab, there is an option called table. Okay, so if I double click this table, the table comes over here and it gets connected to the EFA, or if I just drag and drop over here the table, and then I need to connect these two nodes. As I've told you, it's basically depends on how you are developing the internodal connect. So each and every node has to be connected. So you select this, right click this, connect, and then you just drag it. Okay, so it is connected. Now you double click this table, okay, and you simply run. There is an option over here to run this table. Now you see your entire data set will be reflected. So I have 98 number of observations. You remember that we have used this example a few minutes back. So 98 sample size with 12 variables, all are inserted. Okay, so let me just close it. So this is the table that I have brought. Now let me go to the field operation because I need to define the type of data. Okay, I have to define the type of data that I am having. So there is a type tab over here. You just bring it over here and then again connect it with the data set. Okay, just draw it here. And now double click and open this type 1. You see all the measurement by default is kept at nominal level, but we know those are all ordinal because those are, so you have taken it with the help of a Likert scale. So let us change these things into the ordinal measurement. Definitely these are not nominal at all. So there are 12 variables and I am changing all this to the ordinal measurement. Okay, so everything is done ordinal. Now in the value column, you will find the value columns are unread. That means you need to read these value. Okay, so value means what value these data set represent. That means out of a scale value of 1 to 5, what exactly the value for these particular variable. So there is a tab over here which is called the read values. So I need to click this. As soon as I have clicked this, you see all the value rows are populated. And the last column, which is very important, all these are input variable that we have already seen. Since it is an interdependence technique, there is no target variable. Okay, so apply and okay. So we are done with this. So let us see the output. Say, let us go for the statistics first. Okay, so let us pull down all the variables. Control A. Okay, so all the variables are populated. We want to check all mean, mode, median, standard deviation, etc. Apply and then run. Okay, now you can see the results. Okay, so all the descriptive statistics if you are interested to check. Now the second thing that we want to do is go to this modeling tab and you just go for this one, this PCA oblique factor. You see this one is the thing. So you can connect it with the type and then let us go here. Let us populate the variables first. Select the first one, go for Control A, go for OK. All the variables are populated. Go for model. We are using the principal component. Expert, you select this expert option. We go for correlation matrix, eigenvalues over 1, fine. You sort the variables, you hide values below, say, 0.60, and the rotation that you will be using is Variance. Okay, so it's okay. You apply. Then there is a button over here which is called run. So you just run it. You see the green arrows are signifying that the process is being run. So the modular function basically uses the internodal connectivity. If the node connectivity is done properly, then you will get a very beautiful result, almost similar to that of what we have received in IBM SPSS, the normal function. So you have got this nugget. This nugget is basically nothing but the output thing. So if you double click it, and if you expand this and you go to these advanced stages, so you get everything. Okay, so total variance explained. See, the figures are all absolutely same, 71.493 or something like that. The rotated component matrix, again, there is a 4-factor solution. You can check, cross-check the factor loadings. It will be same. So we need basically these these few one. For the Kmos test and the Bartlett's sphericity, there are certain other parameters there, so you can test it for them also. So these can be tested. This can be done with the help of the factor analysis can be taken up with IBM SPSS model. Now, one very advantageous thing for IBM SPSS modeler is if you want to convert the interdependence technique into a dependence technique. That means if you are in a position to identify at least 2 factors which can be used for a targeted variable, you can apply any kind of a predictive analytics over here. So you can apply artificial neural network, or if you want to classify, you can go for logistic regression. If you want to identify which is the nearest competitor, you can go for KNN, or the K nearest neighbor analysis. So on a single platform, after doing the initial finding out the initial solution, you can go for any kind of dependence technique. So that is one of the advantages for the modular function. Okay, so I have just shown it because these modular functions are now being used on a regular basis by the industry, particularly the e-commerce site like Flipkart and Amazon, for very high degree of predictive analytics and finding out the search behavior, consumer decision making processes, the RFM, the recency, frequency, monetary kind of a model, consumer basket analysis or market basket analysis, etc. So they are using it, and this has become. We are also using it for any kind of advanced analytical process. So this can be used also. Okay. So with that, we conclude the first session. So if you have any question, you can ask me right now, or we can take up the question after, say, the second session. In the second session, we will be dealing with the confirmatory factor analysis. And then if you have any question, you can jot it down right now and you can ask me after the second session.